So, Assalamu alaikum, everyone.
Walaikum assalam.
Just wait a minute or so to see if anybody else joins.
At least a couple of people join. अभी तो सिर्फ हम दोनों ही हैं.
So, can you see the screen?
Yes, yes, yes.
Okay. So, I think we can start. Don't seem to. Okay, so we were talking about the data link layer, and just one announcement: we'll be having our last exam, inshallah, this Sunday. This will be the 9th exam in the series. Once again, same time duration, 20-25 minutes, in a slot between 4 and 4:30 p.m. on Sunday afternoon. We were talking about the data link layer last time, and we said that the data link layer is responsible for transmitting your IP datagram one hop away. So it's the layer which is technology dependent and is responsible for basically delivering your frame one hop away. And because it's technology dependent, basically what you have is you're providing a frame, which means that a header and typically a trailer at the end of the payload, which is your datagram, IP datagram, network layer datagram. And over here, you have the key challenges that one has over here is that depending upon the topology of the network, whether it's a point-to-point link or a point-to-multi-point link, you have different challenges. And one of the key challenges is when you have a point-to-multi-point link is that who is going to transmit a frame when, and you have to coordinate this. So broadly speaking, you have schemes which allow some kind of a random access to the medium where anybody can transmit whenever they have data to transmit. And that causes problems because if you have two or more stations simultaneously transmitting, then they could both try to use the medium at the same time, which will result in a corruption of the transmitted frames. And when the receiver receives that data, it will not be able to discern clearly कि जी क्या frame मिली है. So you have this problem, and then you have to sort of prevent against that, and that is essentially the problem of medium access control, that who gets to access the medium, who gets to access the channel at what particular time. Similarly, if your frame is transmitted over a lossy medium, then there's a possibility that it gets corrupted. Along the way, bits get flipped because of noise, and due to that, you have to have some kind of a mechanism for, first of all, being able to detect errors, and then if you detect an error, also to then maybe if you're using some advanced coding techniques, to be able to correct some of those errors. So error correction and detection um, is what you would want to do. So the key issue over here is reliable delivery between adjacent nodes. And uske liye you also then want to have some kind of mechanism for flow control, which is spacing between adjacent sending and receiving nodes, so that the sender does not overwhelm the receiver. And we've just talked about error correction and detection, as well as issues such as who gets to transmit when, whether both stations are transmitting simultaneously and receiving simultaneously, or only transmit at one given time, and while transmitting do not receive. So that's a half duplex mode in which each station can transmit or receive, but only do one thing at a time. So the key issue over here is that you have some adapters, and these adapters basically take the datagram and frame it with headers, bits, and trailer bits, and then modulate that for transmission over the physical medium appropriately. So it's typically implemented in hardware, in a network card, which does all of that for you. And on the receiving side, once again, you have a hardware adapter or a network card, which basically receives that frame, receives the signals, works out कि जी ये signal कहाँ से शुरू हो रहा है, कहाँ खत्म हो रहा है. So it could be sort of synchronized to some common clock. It could be asynchronous, where you don't have a common clock. So then you have to detect कि जी frame start कहाँ से हो रहा है, and you have interesting techniques in the physical layer which basically detect कि जी frame कहाँ से आ रहा है by using special signals called pilot signals, and techniques in communication which actually help you to actually detect the beginning and end of the frame, and then figure out कि ये जो signal है exactly ones and zeros के अंदर ये क्या है. So basically the link and physical layers are what we're talking about. And उसमें पहली चीज जिसको discuss किया था last time, that was error detection. And for error detection, we said that, well, if you have a datagram of, let's say, D bits, you're going to add some additional bits, which are error detection and correction bits. These are additional bits that you add. And when you transmit this channel, when this frame over a bit-prone error link, some of these bits might get flipped. What you receive is not D, you'll get something which is something different here, which is D prime. And you could also have bit flipped in the checksum over here, or in these error detection and correction bits. And then because you know कि ये error detection and correction bits किस algorithm के तहत calculate किए गए थे, you independently calculate those based upon the data that you've received, and उससे verify होगा कि ये आपको जो चीज मिली है ये ठीक है या नहीं है. And if all the bits in D prime are okay, then the datagram is sent up to the higher layer, which is the network layer. Otherwise, an error is detected. Now, once an error is detected, then depending upon किस किस्म का error है, you might have to drop the entire frame, or you might be able to recover from the error by correcting the error. So we talked about parity bits, and the parity bits, you basically detect single bit errors, and usme you can have two schemes, odd parity or even parity, where the parity bit that you set will result in the total bits being odd or even. And then we talked about a two-dimensional parity bit scheme through which you can recover a single bit error, because when an error takes place at the intersection of the row and column, वो corresponding जो चीज है वो आपके पास, that is where you're going to have you'll be able to detect that where that took place, because when that bit is flipped over here, the corresponding row will result in an error, as well as the corresponding column will result in an error. And basically, when you transmit these bits, you transmit them in a long frame, but the corresponding positions actually correspond to कि ये आपके पास ये जो भी words आपने भेजने हैं उनको उनके end पे आप ये append कर रहे हैं, so that's how it's going to be structured. And then you'll have some column bits which correspond to the appropriate position as if you had sent them a sort of column wise, and वो जो you work out this last word over here based upon the column bit parities, and therefore when one bit gets corrupted in that frame, ठीक है, तो correspondingly उन positions के ऊपर रो बिट पैरिटी के अंदर भी एंड जो एंड पे आपके पास कॉलम बिट पैरिटी का वर्ड होगा उसमें भी you will detect that particular error over there, and therefore by looking at those two positions you will know that this particular bit has been flipped, and then you can correct that. So this two-dimensional scheme allows you to correct a single bit error. Now we'll talk about checksums, and isme the most commonly used one is the CRC, or the cyclic redundancy check. Now isme basically what you're doing over here is that you're viewing the data bits D as a binary number, and then you're adding some additional bits over here which are G bits, ठीक है, and ये जो G bits हैं ये आप लेते हैं कि based upon a very interesting sort of math which allows you to then detect and correct errors. And usme basically if you choose to have R bits which you're going to add or append at the end of your binary number, so you're appending R bits to your D bits, ठीक है, so जो आपने word भेजना है या message भेजना है, that contains D bits, you're appending R bits to the end of that, ठीक है, and these R bits that you are appending to the end of that, ठीक है, are such that these are your original D bits और आपने इसके end पे R bits append कर दिए. So these are your CRC bits that you are appending. Now these CRC bits that you are appending, you can think of them as being calculated in a very special way. Okay? And so what are the sort of possibilities that one might have in designing these CRC bits? So एक चीज तो ये कि, for example, you might have checksums. Now you can think of this that, okay, you're transmitting a message, D bits, okay? Now that can be represented as a binary number, okay? And let's say you were transmitting a number of these words. So अगर आप उन सब words को add up कर लेते हैं using maybe say 1's complement arithmetic, you would get a sum. So if you sent that checksum along, that would be one way of doing it. But it is possible that you have errors in a way such that if you bits are flipped in such a way that your checksum still remains valid. That's very possible. So for example, if I had, let's say, two numbers, let's say I was transmitting a 5 and a 4, and the sum becomes a 9, then if the bits get flipped in a way that the 5 becomes a 6 and the 4 becomes a 3, the checksum will still remain the same. So you've got to do something a bit more clever than a simple checksum. So what can be done? And mathematicians have actually come up with some very interesting coding techniques which allow us to sort of which allow us to detect as well as correct some very sophisticated sort of or commonly errors that take place. So usme basically what you have is you're going to choose a special bit pattern generator G, that अगर आपके पास R bits हैं in what you're appending at the end as the CRC bits, so the generator is one bit more than that. It's an R plus one bit generator. And the way it works is that you have some number, ठीक है? और जब आप इस number को sort of, let's say, आप इसके end पे, let's say, पहले आप zeros लगा दें, ठीक है? R zeros लगा दें. Now, adding R zeros to the end of a number in binary is the same as multiplying it with 2 raised to the power R. Okay? So that is the same as multiplying it with 2 raised to the power R. Now, इसके बाद आप क्या करते हैं कि suppose ये जो number आपके पास आया, आप इसको divide करते हैं with the generator G. ठीक है? And whatever is the remainder, we'll call that remainder R. ठीक है? Now, if this was perfectly divisible by the generator G, then of course your remainder is going to be all 0 bits over here. Whereas if it was not, then if you appended the remainder over here, then what you get, this D and R bit combination, this D plus R bits that you get, is going to be perfectly divisible by this generator G. Okay? So basically what you're doing is that you're taking these D bits, unke end pe aap zeros laga rahe hain pehle, you're doing a calculation and dividing this by the generator, and you're getting a remainder. And then this remainder over here, you're appending over here so that these D plus R bits are perfectly divisible by this generator G. So that's what you're transmitting. On the receiving side, when you receive these bits, what you do is you basically check and see that whether these D plus R bits are perfectly divisible by G. If they are, then you know that there have been no errors over here. If they are not, then you know that you have errors in what has been transmitted. Now, the theory tells us that if you choose G carefully, okay, then this is going to be able to detect interesting combinations of errors. So you'll be able to detect maybe all 2 consecutive bit errors, okay, or even more advanced things than that, okay. So the math helps us in actually designing our checksums, our CRC bits, using carefully chosen values of G, which will sort of cater for all of those possible bit errors. So not only single bit errors, but more than single bit errors को भी आप पकड़ सकते हैं using this carefully chosen value of G. Now, इसके लिए जो math है वो काफी interesting है, and what you see is that by adding just a few bits, I mean, if you see how we design these using coding theory, let's say you have a message which is 32K, by adding just a few bits, maybe 32 bits or 16 bits, CRC 16, CRC 32, by adding less than 0.1% bits, okay, what you can do is that you can prevent or detect a large set of errors. So these are very, very sort of clever and interesting sort of mathematical techniques which allow us to do that. अब इसके पीछे जो math है वो यही है कि what you want basically is that ये जो आपके पास original number था जो आप भेज रहे हैं D bits shifted by R bits, this is the same as multiplying with 2 to the power R, ठीक है? इसको आप basically you are dividing by G and essentially जो आपका remainder आ रहा है वो अगर आप इसके साथ append कर दें, ठीक है? So that is what you're transmitting. So then this thing over here, the shifted bits plus the remainder is perfectly divisible by G, and your quotient is going to be N. Okay? And so basically these R bits that you add or append are your original bits shifted by R, and you divide them by your generator G. Now, what this allows you to do is the following. It can detect all single bit errors. It can detect all double bit errors as long as the generator has at least 3 bits. Any odd number of bit errors. Okay? So if you have any odd number of bit errors, 1 bit errors, 3 bit errors, 5 bit errors, as long as 1 divides into G, and we'll see what 1 over here means. Okay? And any bursts of length smaller than G and most larger burst errors ये है कि when you have 1 bit corrupted and then you have a sequence of other bits and then you have another bit corrupted, and in between this sequence of all bits, all of them could be corrupted or most of them could be corrupted, but you have basically more than 1 consecutive bit error. You have a burst of errors, burst of bits which are in errors. So most bursts larger than a few bits are also sort of detected. So these are very, very sort of powerful techniques. So the way this works is we'll show you. suppose आपने जो original message था, the D bits that you wanted to transmit were these bits over here. So you want to transmit 101110. You want to transmit these 6 bits. Okay? And we will transmit these 6 bits by adding 3 additional bits over here, which are these, which we'll append. Okay? So the first thing that one does is that you multiply this original D that you want to transmit with 2 to the power R, which is the same as adding zeros at the end, R zeros at the end. So in our design, D is 6 bits and R is 3 bits. We've added these 3 zeros at the end. This is the same as multiplying D with 2 to the power R. Okay. So R calculate करने के D to the power 2, D multiplied by 2 to the power R को you're dividing that with your generator G. So our generator should consist of R plus 1 bits. So our generator over here, we've chosen that to be 4 bits, R plus 1 bits, 4 bits, which is a 1001. ठीक है? So ये जो number है, इसको आप divide कर रहे हैं with 1001. ठीक है? Now the division that we're doing over here is a ones complement division. Basically, the mathematical theory behind this is of what you call finite fields. So usme, we all know that field kya cheez hai? Field is basically the set of numbers that you have in some algebra. So in any algebra, basically you have to, as long as you can consistently define what addition is, what subtraction is, what multiplication is, and division is, and as long as the properties hold, you have commutation over there, you have association over there, you have a additive inverse, you have a multiplicative inverse, you have the distributive property which holds. So ये चंद set of properties अगर आप define कर सकते हैं over a set of numbers, ठीक है? Then that the entire rules of algebra hold over there for that particular field. So ये जो field हम define करेंगे, this is going to be for 1 and 0. And the way it works over here is that जो regular addition subtraction है, उसमें तो आप borrow कर रहे होते हैं और add कर रहे होते हैं. But the field that we want to define over here is such that a 1 plus 1 is a 0. So I'll just very quickly just write down these rules for us. Okay. So the algebra that you want is a 0 plus a 0 is going to be a 0. A 0 plus a 1 is going to be a 1. A 1 plus a 0 is going to be a 1. And a 1 plus a 1 is going to be a 0. And we won't have any carries over here. ठीक है? इसी तरह से a 0 minus a 0 will be a 0. 0 minus a 1 is going to be a 1 with no borrows. ठीक है? A 1 minus 0 will be a 1, and a 1 minus 1 is going to be a 0. ठीक है? So the interesting thing over here is a 0 minus 1 is a 1, and you are not doing any borrows. Okay? So with this set of addition and subtraction rules, हम अगर ये division करते हैं, ठीक है? Let us not talk about multiplication and division for the moment because we don't need that. So we see that, okay, let's divide this number with this generator here. So we'll go once, you put a 1 up here, and long division आप करते जाएं. When you put a 1 up here, you'll have a 1001 below this. Now using these sets, one's complement जो आप sort of subtraction आप कर रहे हैं, अब 1 minus 1 is a 0, a 1 minus 0 is a 1. These two match up, so ये zeros आ जाएंगे leading. You'll bring the next number down, which is a 1, so you get a 101. Obviously, this 101 is smaller than this, so you put up a 0 here, and then you bring the next number down, which is a 0. So now you have a 1010. Up, you can put up a 1 up here, multiply this with this, and you get a 1001 over here. Now, once again, you do the subtraction. So when you do the subtraction, a 0 minus a 1 is a 1. No borrows. Okay? A 1 minus 0 is a 1, and you get 1, 1 here. Once again, you bring down the next number, you get the 0 here. This is smaller than that. You put up the next 0, and you bring down the next number here. So you get a 1, 1, 0, 0. Okay. You could have done this in one step, but for completeness, we've shown that when you put up a 0, you're actually putting up a 0 here and then subtracting, but you could have done this in one step. Then you do the subtraction, and of course, you get a 1, 1, 0. Bring down the next number, which is a 0. And this time, of course, you're going to put up a 1 and write a 1, 0, 0, 1 over here. Do the subtraction. Once again, a 0 minus a 1 is a 1. 0 minus 0 is a 0. A 1 minus 0 is a 1. Bring down the next number, 0. And you put up a 1 up there. And you multiply this 1 with this. Once again, simple long division rules here. 0 minus 1 is a 1. A 1 minus 0 is a 1. And then you have 0. 1 minus 1 is a 0. So you're left with these 3 bits over here at the end, which is your final remainder. So what you then do is that you take these 3 bits and exclusive OR them with these 3 bits at the end over here. So then essentially what you're doing is जो D bits हैं उसको आप append कर रहे हैं with this remainder, which is a 0, 1, 1. So what you transmit is a 1, 0, 1, 1, 1, 0, followed by a 0, 1, 1. And that number is perfectly divisible by your generator. It's perfectly divisible by your generator. Okay? Right, so any questions over here? Any questions? Okay, and any questions regarding this algebra of ours? You are doing finite fields. The field that you have is a 1 and a 0. And you're defining these rules of mathematics, or the complement wale hain, directly, such that what you're defining is a 0 minus 0 is a 0. And this up here, just once again for you, because this is the really interesting part. With no borrows, a 1 minus 0 is a 1, and of course a 1 minus 1 is a 0. So this is the...
Hello, अस्सलाम वालेकुम सर.
वालेकुम अस्सलाम. जी.
सर ये हमने G कैसे select किया है?
अच्छा, ये जो G आप select करते हैं कि 1, 0, 0, 1, इसके पीछे मैथ है, ठीक है? And उसमें जो interesting bit है वो ये है कि basically ये जो आप चीज represent कर रहे हैं ना, let's say the D bits that you want to transmit, ठीक है? You can view this as a polynomial, ठीक है? Polynomial किस तरह से कि let's say ये number है, ठीक है? तो this 0 bit over here represents 1s. This represents 2s, this represents 4s, this represents 8s, this represents 16s, and this represents 32s. ठीक है? Now, एक तो ये representation है इसकी binary के अंदर. अब इसी चीज को मैं uniquely लिख सकता हूँ as a polynomial, where I say that this represents x to the power 0, this represents x to the power 1, x to the power 2, x3, x4, and x5. So I could write the same number out in mathematical form as x plus x squared plus x cube plus x5. ठीक है? That's a polynomial expression. और polynomial expression के अंदर ये जो 1 and 0 है, ये आपका sort of coefficient है of that polynomial. ठीक है? So in sort of, so what you're doing over here is I could represent that by one polynomial. ठीक है? Now, if you think about this, it's perfectly valid to represent that with that polynomial. The x could be anything. ठीक है? x का मसला नहीं है. उसकी वजह ये है कि इस नंबर को आप यूनिकली रिप्रेजेंट कर सकते हैं उसके साथ. एंड जिस तरह से उन पॉलिनोमियल्स के ऊपर आप ये सारे रूल्स एडिशन सब्ट्रैक्शन के डिफाइन कर सकते हैं, दैट ऑल ऑफ दैट अलजेब्रा इज गोइंग टू वर्क ऑन दैट पॉलिनोमियल. ठीक है? फिर आप उसको डिवाइड करें इस जनरेटर के साथ, और इसमें वंस अगेन ये 1s हैं, 2s हैं, 4s हैं, 8s हैं. ठीक है? या फिर x to the power 0, x to the power 1, x to the power 2, x to the power 3. So I can write this polynomial here over here as x cube plus 1. X cube plus 1. ठीक है? Now, so the interesting thing is कि जिस तरह से आपने लेट अस से ये जो पॉलिनोमियल है, आई जस्ट राइट इट आउट फॉर यू, ये हाईएस्ट पावर आपके पास 0 1 2 3 4, सो दिस इज x टू द पावर 4, ठीक है, मैं अभी इस पावर्स को ठीक से ही कर लूंगा, प्लस x स्क्वायर x4 प्लस x स्क्वायर प्लस 1, ठीक है, ये नंबर है. I'll just put this up over here as a ठीक है जी. ये आपके पास एक पॉलिनोमियल आ गया, x4 प्लस x स्क्वायर प्लस 1, ठीक है. अब इसको अगर आप डिवाइड करते हैं, so with this other generated polynomial here which is x cube plus 1 के साथ, ठीक है. So I'm dividing this here, I'll just divide this here with an x cube plus 1. That's what you're doing over here. It's the exact same process. ठीक है, ये आप डिवाइड कर रहे हैं. So you can define this algebra using polynomials like this. So the question really is that ये आप ऐसा चूज करें that जब इस चीज को आप डिवाइड करते हैं, इसको आप ब्रेकअप करते हैं, ठीक है, तो जो आपके पास रिजल्ट आता है वो ऐसा है कि यू आर एबल टू फिगर आउट के मसला कहाँ पे है. नोटिस कि यहाँ पे आपने ये 3 और जीरोस ऐड किए, तो फिर दैट्स गोइंग टू शिफ्ट दिस एंड ये पावर चेंज हो जाएगी, बट essentially what you're doing is you're dividing these polynomials. Now if you think this, अगर let's say आपके पास ये जो ओरिजिनल नंबर था ये इस किस्म का पॉलिनोमियल है, all ones है यहाँ पे, so you'll have a maybe an x7 plus an x6 plus an x5 plus so इस किस्म का पॉलिनोमियल आपके पास आएगा, ठीक है. You want to divide it with such a number over here such that you will be able to detect, let's say, 1-bit errors or 2-bit errors. So you need to think, अच्छा जी, 1-bit error होगा, so what will happen to this number? अब 1 will become a 0 or a 0 will become a 1. So essentially ये जो आपके पास coefficients हैं यहाँ पे, ये coefficient 1 है यहाँ पे and x का coefficient 0 है, वो shift हो जाएंगे. ये x स्क्वायर की टर्म खत्म हो जाएगी और x की टर्म आ जाएगी, ठीक है. That would be a 1-bit error, that some of these terms would flip, ठीक है. So when you divide something with something like x to the power I plus 1, ठीक है, what you're going to get over here in your remainder, you want to come up with a design such that you're able to detect these errors. Question ये कि error detect कब नहीं होगा, because let's say कि आपके पास you were dividing something with let's say 4 only, a 1 0 0. तो जब आप 4 से डिवाइड करते हैं किसी चीज को, तो it's perfect, what numbers are perfectly divisible by 4? So you will see कि अच्छा 4 के साथ 4 भी perfectly divisible है, 8 भी divisible है, 12 भी divisible है, 16 भी divisible है. Any multiple of 4 is divisible by 4, ठीक है. So अगर आपके पास ओरिजिनल नंबर कुछ भी था, अगर एरर इस किस्म का है कि उसमें 4 का फर्क पड़ता है, तो जो नया नंबर आएगा वो भी परफेक्टली डिविजिबल होगा, रिमाइंडर पे फर्क नहीं पड़ेगा. ये बात समझ रहे हैं. लेकिन अगर आप लेट अस से प्राइम नंबर्स इस्तेमाल करते हैं, तो अब अगर आपका जनरेटर प्राइम है, तो देन जो नंबर आपके पास है जब आप उसको डिवाइड करते हैं विद अ प्राइम नंबर, सो देन द चांसेस आर कि जब एरर होगा, so you're getting an error which is a multiple of a prime is very smaller, ठीक है? So if you choose, let's say, the largest prime number जो कि आप represent कर सकते with this many bits as your generator, so then जब errors होंगे, the chances कि जब वो जो नया number error के बाद बना है वो भी इस prime number से divisible है, that is going to become much उसकी probability will be much smaller. ठीक है? So basically you're using a lot of mathematics theory to actually cleverly select and design your generator such that error होंगे, 1-bit errors होंगे या 2-bit errors होंगे या odd bit errors होंगे, तो आप उन errors को पकड़ पाएंगे. ठीक है? So that's the math behind it. There's a lot of mathematics behind this, and people over the years have sort of been able to design these, and it's not easy to come up with new of these. क्या कहते हैं ना, ये नए इस तरह के नंबर ये पकड़ना इतना आसान नहीं है. So I mean, mathematicians have over time designed these CRC checks. ये अगर आप can you see my screen?
Yes, sir.
You can see these polynomial representation of cyclical redundancy checks. ठीक है? So, for example, x plus 1 would mean 1, 1. ठीक है? ये इसकी would mean a CRC1 would be x plus 1, which means that both of these bits over here are a 1. And इसमें ये इनकी properties दी हुई हैं आपके पास. अब ये जो CRC8 में you're using this number over here, this is a 1, 0, 1, 0, 1, 0, 1, 0, 1, 1, 1. So 1, 1, 1, 0, 1, 0, 1, 0, 1. This is the generator that you're using, and this is its equivalent sort of polynomial form. So इनकी ये properties दी हुई हैं. तो ये जो है ये Bluetooth में for example इस्तेमाल हो रहे हैं. CRC32 जो है आपके पास, CRC16 इन सारे standards में इस्तेमाल हो रहे हैं, और this is the check. So very simple generator. It's just 1, 2, it's a 16-bit generator. ठीक है? And if you work out these certain very interesting properties of these, एक property को Hamming distance कहते हैं. वो ये है कि उतने कितने bits consecutive हो तो यानी you can detect that error. So a CRC32 check, for example, if you look at this property over here, ये जो है कि maximum bits of payload by Hamming distance. तो इस पे you can basically detect कि payload का कितना size जो है, which is a huge number of bits over here, of possible error types that you can detect over here based upon the CRC32. So it's very efficient. And इससे बेहतर जो आपके पास checks बने हैं of recent, वो are these ones over here. ठीक है? And इनकी performance जो है ना उससे भी अच्छी है. But actually design them is math. ठीक है? And mathematicians and coding theory people have designed these over time. And फिर इनकी properties निकाली है कि ये क्यों अच्छे हैं. And the incredible thing about these checksums is that by adding 32 bits or 16 bits to a frame which is in kilobits, 32 kilobit long frame में आप सिर्फ 16 bit add करने से आप बेशुमार किस्म के errors पकड़ सकते हैं and correct भी कर सकते हैं. So that's why they have been very cleverly designed by these mathematicians, and they are implemented in hardware. Okay. So वही चीज है, जैसे as an example I said, if you divide a number by a prime number, so then what happens is that when those errors take place, जो नया number आएगा, it's not going to be divisible by a prime. But if you did not carefully choose your generator, तो फिर जो नए numbers आएंगे वो भी divisible होंगे and आप उन errors को पकड़ नहीं पाएंगे. Okay? So this is just a sort of a, yani, I would say a not very comprehensive result, but if you're interested, I mean, you can look up the math to see कि ये कैसे design किए गए हैं and ये कैसे चल रहे हैं. Okay, so any further questions? Okay, so we talked about what errors can be detected earlier. We said that CRC can detect all single bit errors, all double bit errors, as long as the generator has at least 3 ones. Now, this is a mathematical property which you can prove that अगर आपके polynomial में कम से कम 3 ones हो, you can detect all double bit errors. Now, it doesn't say consecutive double bit. Any 2 bits anywhere in that entire sequence, you can detect them. Any odd number of bit errors, which is amazing, 1 bit, 3 bit, 5 bit, उन सबको आप पकड़ सकते हैं. ठीक है? As long as x plus 1 is a factor of the generator polynomial, which means that you can factorize the generator polynomial into x plus 1 multiplied by something. Okay? So these are some very, very powerful properties of the CRC checksums. Okay, so that's about what we want to talk about or what we want to say about CRC. The idea यही है कि आप additional bits भेज रहे हैं, and those additional bits have been designed in a very clever way, and उन चंद bits से आप ना सिर्फ errors detect कर सकते हैं बल्कि कुछ को correct भी कर सकते हैं, and these are sort of उससे आपको पता चलता है कि the frame that you've received is correct or corrupted. The next thing we would like to talk about is multiple access links and protocols. Now, there are 2 types of links, point-to-point and broadcast. Point-to-point में ये है कि जैसे dial-up में आपके पास एक end है and you have some channel and then you're connected to the other side of the channel. जो भी आप transmit करते हैं वो receive किया जाएगा, जो transmitter भेजेगा दूसरे end से आप उसको receive करेंगे. So it's a point-to-point link. इसी तरह से ईथरनेट स्विचेस के अंदर ईथरनेट स्विच और आपके दरमियान एक केबल रन होती है, Cat5 Ethernet cable. Mostly it could be a fiber optic cable as well in sort of if you have a fiber based Ethernet switch, but otherwise that is going to be a point to point connection. Okay. Broadcast, you have a shared medium or a shared wire. Old fashioned Ethernet में जब आपके पास you had a coaxial cable running and then you had these vampire taps into this coaxial cable. That was the original Ethernet that one had, which ran at 3 megabits, subsequently 10 megabits per second Q per year. You had something called a standard called 10 base T. So this is a shared medium. Whenever you put a signal on this cable, everybody else can listen to that medium. That's why we call that, listen to the signal that you're transmitting. That's why we call that a broadcast medium. इसी तरह अगर आपके पास वाईफाई कनेक्शन है तो एक वाईफाई राउटर यहाँ पे है, and जो ये सिग्नल भेज रहा है, anybody in this region can receive that signal. So it's a broadcast medium. जब आप एक सिग्नल ट्रांसमिट कर रहे हैं, anybody can receive that signal, can eavesdrop on that signal in your vicinity. So this is a shared radio channel that you're using. Okay? And an example of this shared radio frequency RF medium that you're using is the one that you have in Ethernet Wi-Fi. And similarly, shared RF medium आप इस्तेमाल कर रहे हैं जब आपके पास एक satellite link है, and that satellite link is potentially is being shared, who sort of puts up a dish and they can access this shared medium. And the analogy, of course, is that just like you have many people talking in a room, okay? So because when one person is speaking, all the other people can listen to that person. the air interface that you have, the acoustical interface that you have is a shared medium. ठीक है? So broadcast में जब एक बात कर रहा है तो सारे सुन सकते हैं, and उसमें मसला फिर ये है कि multiple people can speak at the same time, which will result in unintelligible speech. तो मसला हो जाएगा. So that's the exact same challenge that you have in a broadcast or shared medium, where if more than one of these stations is putting out a signal simultaneously, then the signals are going to get mixed up, garbled, and you will have a problem. So you have to have some kind of medium access control protocol hona chahiye, which should describe who gets to talk when. So when you have a single shared broadcast channel, okay, and two or more simultaneous transmissions by nodes, then you have interference or collision, and then you need to have a multiple access protocol, which defines that jab multiple log hain, so how do they get access to the shared medium? So this has to be a distributed algorithm that determines how nodes share the channel. That is, who gets to transmit when. And मसला उसमें ये है कि जो communication आप करेंगे about sharing the channel, वो भी उसी medium को इस्तेमाल करेगी, and therefore that can also get garbled. So the idea is that you cannot have an out-of-band channel for coordination. ऐसा नहीं है that you have a separate network जिसके ऊपर आप coordination कर रहे हैं, and you have, because otherwise you'll have to have multiple sort of extra capacity, extra bandwidth, one for the coordination and one for the communication itself, and that is going to result in more capacity required. And for efficiency purposes, you want to be able to do the communication on that same channel, ideally. So suppose you had a channel of rate R bits, capacity R bits. So when one node wants to transmit, it can send at rate R. And if you have M nodes, then each can send at an average rate of R divided by M. ठीक है, so M nodes अगर हैं, जब वो भेजेंगे तो full burst rate पे भेजेंगे R पे, लेकिन they can only transmit for 1/m of the total time. So therefore, the average rate that each gets is R/m, and that's the best that you can achieve. Now, if you have a decentralized model, then you'll have no special node to coordinate these transmissions, and you will have no synchronization or clocks or slots, and it's going to be simple, but the challenge, of course, is going to be कि ये आपके पास who gets to transmit when, collisions होंगे तो कैसे उनको handle किया जाएगा. Alternatively, you can have one special node for transmitting or coordinating the transmission, I should say. Or वो ऐसे है कि that could be a master and it could only give control over or let the other stations transmit by granting them permission. या आपके पास कोई special slot है कि जब वो slot आपके पास हो तो उसी आप अपने slot में ही transmit कर सकते हैं, बाकी हमें नहीं कर सकते. वो achieve करने के लिए you'll have to have some kind of a common clock, which is also a challenge in a distributed system, and ताकि सारे synchronized हों. And synchronizing multiple stations is also a challenge in a distributed system. So you need to have common clocks, you need to have then synchronization between those different stations, and then you'll have to have some coordination technique कि कौन कब बात करेगा, हर एक को एक fixed slot दे सकते हैं, and these nodes only transmit in their fixed slots. या कोई और protocol आपको evolve करना पड़ेगा कि जी इस set of rules के तहत आपकी communication होगी. So the sort of broad classification that one has, there are three broad classes. एक ये कि channel partitioning है, where you divide the available capacity, the available channel into smaller pieces. These could be time slots, they could be frequency, they could be different codes, and इसकी basis के ऊपर आपके पास ये different techniques हैं. Time division, multiple access, frequency division, multiple access, and code division, multiple access. और आपने हर एक of node को एक particular time slot या एक पर्टिकुलर फ्रीक्वेंसी एलोकेट कर दी है, वो उसी के अंदर ट्रांसमिट कर सकती है. ये एलोकेशन कैन बी थ्रू सम coordination function, through some control channel. And once this has been decided, to then for that communication आप वही time slot या वही frequency आप इस्तेमाल कर रहे हैं. No one else is using that. So you're basically partitioning your channel capacity and you're allocating one piece of this capacity to that particular node for exclusive use during the communication. दूसरा ये है कि you provide random access. ठीक है, random access में the channel is not divided, so then collisions can take place. So if a collision takes place, then you'll have to recover from collisions, which means that अगर दो स्टेशन simultaneously transmit कर रहे हैं तो collision हो गया, तो आपको collision detect करना है कि collision हो रहा है, and then जो transmitting stations हैं उनको कहना है भाई रुक जाओ, they'll have to stop and they will have to then retry after some time. Now if they retry after the same time फिर collision होगा. So typically what you do is you have some kind of mechanism which that when they retry after a random amount of time. And even more interestingly, before they actually try, जैसे कि आप बात करते हैं, तो बात करने से पहले आप सुनते हैं कि कोई और तो बात नहीं कर रहा. अगर कोई और बात नहीं कर रहा, फिर आप बात करते हैं. So basically you have some kind of a carrier sense mechanism which checks to see whether somebody else is using the channel. If the channel is free, then you transmit. But it's still possible that if two stations sense that the channel is free and they both simultaneously start transmitting, ठीक है, फिर भी collision हो सकता है. Because, and why does this happen? Because any thoughts on this? That दो बंदे बात भी कर रहे हैं, तो ये भी हो सकता है कि वो दोनों सुनते हैं, खामोशी है, दोनों इकट्ठी बात करना शुरू कर दें. एक तो ये है, लेकिन इसकी chances कब ज्यादा होंगे? Any thoughts on this? Collisions के. जी. Any thoughts on this? Any ideas? Are you there, gentlemen?
Yes, sir.
Any thoughts? Collisions कब ज्यादा होंगे?
सर जब नोड्स पे किसी लिंक पे या मीडियम पे कनेक्टेड लोग ना ज़्यादा होंगे तो चांसेस कोलिजन के ज़्यादा होंगे फिर.
ठीक है, so that's very good. So one possibility is that you increase the number of nodes, and when they're all listening, suppose they listen के silent है, तो अगर एक से ज़्यादा try करते हैं communication के लिए because they have data to send, you'll have more collisions if more nodes are connected. दूसरी चीज ये है कि have you done a long distance call?
Yes, sir.
उसपे क्या notice किया आपने?
Sir, delay.
So because of propagation delay, दो बंदे सुनते हैं channel को and they see that the channel is free, because when they listen to the channel it was free, so they can start transmitting. But because of the finite delay it takes for the signal to actually propagate through the network, ठीक है, the larger the physical area of the network, the greater the chances of a collision because of propagation delays of your signals. ठीक है? So that's why typically जितने भी standards हैं, they limit the random access, ये जो आपके पास channels हैं, and they limit the size of the network which is using this random access protocol to a few hundred meters at best. Because beyond that, फिर आपके पास the probability that you're going to have these collisions is going to be larger. So notice that ये जो one hop away हम frame भेज रहे हैं, this is for a local area network. This is for that island जो आप islands को आपस में routers के through connect करके end to end, hop by hop आप packets भेज रहे हैं across the entire internet. So this is one island based upon one technology. So within that island, you will have channel partitioning, or you'll have random access protocols, या फिर you'll have some mechanism where nodes take turns to transmit. ठीक है? So these are three broad categories, broad classes जिसके basis पे आप medium access control protocols को classify करते हैं. So coming back to channel partitioning, TDMA, टाइम डिवीजन मल्टीपल एक्सेस, उसमें आपके पास एक फ्रेम है, आपने उस फ्रेम के अंदर, नाउ दिस इज डिफरेंट फ्रॉम अभी जो हमने फ्रेम की बात की, वो जो फ्रेम है वो बेसिकली एक पैकेट को आपने इनकैप्सुलेट किया और एक फ्रेम बना दी. ये आपके पास ये जो फ्रेम है, दिस इज अ फ्रेम फॉर TDMA, टाइम डिवीजन मल्टीपल एक्सेस, जिसमें आपने हर एक सॉर्ट ऑफ कम्युनिकेशन चैनल को एक इंडिविजुअल स्लॉट साइन कर दिया. तो इन स्लॉट्स की जो सॉर्ट ऑफ कॉम्बिनेशन है जो कि रिपीट करती है आफ्टर अ सर्टेन अमाउंट ऑफ टाइम, that is called a frame. So this is basically a time frame in TDMA, and if let's say you have a 6 slot frame, इसमें से ये 3 slots इस्तेमाल हो रहे हैं, slot number 1, 3 and 4, and they are being used for communication for channel numbers 1, 3 and 4. ठीक है, the blue channel, the red channel and the green channel, ये 3 slots खाली हैं आपके पास. They can be used by some other pair of communicating nodes, and this is called your 6 slot frame over here that you have. Okay, so each station gets a fixed length slot within that frame, and the unused slots go idle. Okay, so if you have another set of users to use, you might want to give them these unused slots subsequently. लेकिन अगर वो इस्तेमाल नहीं कर रहे तो फिर ये slots जो है ना ये खाली जा रहे. So example ये है कि if you have a 6 station LAN, तो 1, 3 and 4 जो nodes हैं have a packets to transmit, ठीक है, and slots 2, 5 and 6 are going to go idle. तो आपके पास एक 6 स्टेशन की LAN है, आपने हर एक स्टेशन को एक स्लॉट दे दिया. तो जिस स्टेशन के पास एक है IP डेटाग्राम टू ट्रांसमिट, वो अपने रिस्पेक्टिव स्लॉट के अंदर उसको ट्रांसमिट कर रहा है, एंड जिनके पास नहीं है तो कॉरस्पॉन्डिंगली उनके स्लॉट्स भी खाली जा रहे हैं. ठीक है. सो एक्सेस टू द चैनल टेक्स प्लेस इन राउंड्स, एंड आप यूं समझ लें कि ये जो आपके पास एक फ्रेम है, दिस कुड बी अ फ्रेम वर्थ 1 सेकंड, मिली सेकंड्स, माइक्रो सेकंड, जिस तरह भी है ये फ्रेम. तो आपने उतने देर बाद फिर आपको दोबारा ये फ्रेम मिलेगी. सो नोटिस, लेट अस से दिस वाज टाइम एंड दिस वाज for example just a 6 slot frame. Each one of these slots is let's say 1 second. ठीक है, तो आपने 1 सेकंड के लिए ट्रांसमिट किया और फिर 5 सेकंड्स ये ट्रांसमिट नहीं करेगा, फिर आप अगला स्लॉट आपको 6 सेकंड्स बाद मिलेगा और आप 1 सेकंड के लिए भेजेंगे. दैट्स हाउ यू गेट 1/6 of the channel capacity. ठीक है, so you're transmitting at the full channel rate, but you're only transmitting for 1/6 of the time, which means that you are transmitting at an average rate of 1/6 of the channel capacity. Any questions here? TDMA में कोई चीज समझ ना आई? ये हमने start में भी किया था in the very first lectures we talked about these slots as well, if you recall. जी, any questions? The next thing is FDMA. FDMA में ये है कि आप जो ट्रांसमिट कर रहे हैं वो डिफरेंट फ्रीक्वेंसीज के ऊपर कर रहे हैं. So these are sort of in parallel transmission चल रही है, but you're transmitting at different frequency bands. So essentially because you're transmitting at a different frequency, receiving side पे आपके पास जो receiver है वो it's going to get separately tune in to its own channel, and you're able to transmit all of that in parallel. Just like radio के अंदर है कि रेडियो पे हर सिग्नल अपने फ्रीक्वेंसी पे ट्रांसमिट कर रहा होता है और आपने एक पर्टिकुलर चैनल पे ट्यून इन करके उस पर्टिकुलर सिग्नल को निकाल लेते हैं, एंड लेकिन ये सारे सिग्नल्स इन पैरेलल चल रहे होते हैं. ठीक है, at a different frequency, and this is called frequency division multiple access, FDMA. So your entire channel spectrum is divided into frequency bands. Each station is assigned a fixed frequency band, and the unused transmission time in frequency bands goes idle. So अगर आपके पास 6 stations हैं, ठीक है, and you've got 3 of them want to transmit so they will transmit at their frequency, and बाकी जो आपके पास nodes हैं, they will not transmit, so वो frequency bands जो है ना वो खाली हैं, they will not be they will not be used. They will not be transmitting. So this is FDMA. Any questions here? Any questions?
Sir, what about the transmission capacity in this case?
देखिए इसमें transmission capacity को work out करने के लिए we can say, well, okay, potentially if all of them had transmitted, ठीक है, then you could be using all of that capacity, ठीक है. Had, for example, 6 different आपने frequency channels allocate किए हुए हैं, ठीक है, and only 3 have data to transmit and they're using that, तो बाकी जो है that's also going idle in some sense. But these stations, because they're transmitting at different frequencies, they are not interfering with one another. ठीक है? In such a system, जब आपने ये decide कर दिया, your limiting factor is the total number of different frequencies that you can use in parallel. ठीक है? Suppose आपने ये system ऐसे design किया कि first come first serve basis के ऊपर जो भी users आ रहे हैं, उनको आप एक frequency band allocate कर रहे हैं. So I have, let's say, 6 available frequency bands for my users. Now, if a 7th user comes in, I cannot allocate that person a frequency band because I have already designated a frequency band for each one of my previous users. So my capacity is limited by the number of frequency bands that I can allocate. Okay? Is this clear? Huh?
Yes, sir.
Great. Now, so random access protocols specify that when a node has a packet to send, it can transmit at either the full channel capacity, okay, and no a priori coordination amongst nodes takes place. So 2 or more transmitting nodes can result in a collision. Okay. So the question then becomes is how do you detect collisions and how do you recover from collisions? And then we'll talk of these examples of medium access protocols. Aloha, slotted Aloha, CSMA, CSMA-CD, and इस तरह से ये और protocols.
सर
जी
सर TDMA और FDMA में सर हमारे पास कोलिजन तो नहीं होगी सर क्योंकि वो एक डिफरेंट फ्रीक्वेंसी पे जा रहा है और वो TDMA में भी एक डिफरेंट स्लॉट पे जा रहा है.
यस तो देखिए यहाँ पे 3 ब्रॉड क्लासेस है ना. क्लास में चैनल पार्टीशनिंग कर दिया. So channel partitioning ensures that आपके पास जो भी चैनल आप allocate कर रहे हैं वो यूनिक है, भले वो टाइम में अलग अलग है या अलग अलग फ्रीक्वेंसी आपने डेजिग्नेट कर दी हर एक को. तो उससे ये है कि चूंकि चैनल आपका यूनिक है, रिजर्व्ड है, ठीक है, तो कोलिजन्स नहीं होंगे आपके पास. लेकिन कॉम्प्लेक्सिटी है इसमें सिस्टम में बिकॉज आपने ये इंप्लीमेंट करने के लिए ये एक स्लॉटेड सिस्टम बनाना है, एक फ्रेम रेपिटेशन रखनी है, एक हर एक को इंडिविजुअल स्लॉट्स देने हैं. वो जो नोड्स हैं दे हैव टू बी सिंक्रोनाइज्ड. एक कॉमन क्लॉक होगी जिसकी ताकि हर एक नोड को पता हो कि अच्छा ये स्टार्टिंग पॉइंट है उस फ्रेम का और मुझे ये वाला स्लॉट एलोकेटेड है. तो फ्रेम जो नोड 1 है वो इस फ्रेम के स्टार्टिंग में पहले स्लॉट में ट्रांसमिट करेगा. नोड 2 को पता है कि मेरे पास ये स्लॉट है, ठीक है, मेरे पास ट्रांसमिशन के लिए कुछ है नहीं, लिहाजा मैं ट्रांसमिट नहीं करूंगा, ये स्लॉट आइडल जाएगा. नोड 3 अपने कॉरेस्पॉन्डिंग स्लॉट के अंदर ट्रांसमिट करेगा. ठीक है, तो ये सारी चीजें जो है ना ये सॉर्ट ऑफ विल हैव टू इस तरह से कोऑर्डिनेट होंगी कि आपको एक कॉमन क्लॉक चाहिए और ये थिंक ऑफ इट कि ये नोड्स डिस्ट्रीब्यूटेड है, ये एक जगह पे नहीं है. तो कॉमन क्लॉक आपस में सिंक्रोनाइज कैसे करेगी, एक अलग चैलेंज है. ठीक है, ताकि ये स्लॉटेड सिस्टम हर एक को पता है कि मैंने किस स्लॉट में भेजना है. अगर वो स्लॉट्स सिंक्रोनाइज नहीं होंगे तो फिर कोलिजन्स होंगे, फिर मसला होगा. तो इसकी जो कोलिजन्स को अवॉइड करने के लिए जो कॉम्प्लेक्सिटी है वो जब तक आप एक कॉमन क्लॉक और ये फ्रेम स्ट्रक्चर स्लॉट्स के साथ इंप्लीमेंट नहीं कर सकते तो यू कांट इंप्लीमेंट दिस सिस्टम. सो दिस provides you collision-free transmission, but at the added complexity of maintaining synchronization and a common clock between these nodes. ठीक है, इसी तरह से FDMA में आप हर एक को अलग फ्रीक्वेंसी दे रहे हैं. फ्रीक्वेंसी डिस्ट्रीब्यूट कैसे करेंगे, हर एक को आप कैसे बताएंगे कौन सी फ्रीक्वेंसी आपकी है कौन सी आपकी नहीं है। हर एक के पास आया फिक्स फ्रीक्वेंसी होगी या उसके पास जो ट्रांसमीटर रिसीवर है इट्स एबल टू ट्यून कि किस फ्रीक्वेंसी पे वो ट्रांसमिट करे। तो यू हैव टू हैव सम कोऑर्डिनेशन कि अच्छा किसको कौन सी फ्रीक्वेंसी देना है। ये भी हो सकता है कि आप शुरू में पहले डिसाइड कर लें कि अच्छा जी आपने इसी पे हमेशा इसी पे करना है, ठीक है। ये भी हो सकता है जैसे रेडियो में होता है कि आप ट्यून करते हैं, यू कैन चेंज योर ट्रांसमिशन एज वेल एज रिसेप्शन फ्रीक्वेंसीज, ठीक है। बट दैट रिक्वायर्स एन ओवरहेड व्हिच इज फॉर डिसाइडिंग कि कौन किस फ्रीक्वेंसी पे ट्रांसमिट रिसीव करेगा। इसमें ट्रांसमीटर एंड रिसीवर की कॉम्प्लेक्सिटी बढ़ जाएगी बिकॉज अगर आप मल्टीपल चैनल्स को पोटेंशियली इस्तेमाल कर सकते हैं, ठीक है। जैसे मोबाइल फोन्स में होता है कि आपके पास एक डिपेंडिंग ऑन द स्टैंडर्ड यू हैव अ रेंज ऑफ फ्रीक्वेंसीज जिसके अंदर से वो एक पर्टिकुलर फ्रीक्वेंसी को इस्तेमाल कर रहा होता है अपलिंक एंड डाउनलिंक के लिए, ट्रांसमिशन एंड रिसेप्शन के लिए, ठीक है। एंड so that is negotiated through a control channel, ठीक है। And the interesting thing in mobile communications way back to even the second generation systems or GSM systems and so on was it was a combination of both PDMA and FDMA. So आपके पास slots थे and then slots के अंदर आप frequencies भी choose कर सकते थे. So that's how you increase the capacity by coming up with that system. But this is overhead, added overhead in complexity, but it provides you exclusive channels, use of right, and no problems जो कि इधर है। ये सिस्टम सिंपलर है, लेकिन कोई भी ट्रांसमिट कर सकता है, लेकिन मसला ये है कि यहाँ पे कोलिजन्स होंगे फिर। तो जो इधर प्रॉब्लम्स अलग हैं, इधर ये है कि आपको सिंक्रोनाइजेशन नहीं करनी है, कोई कॉमन क्लॉक नहीं रखनी है, लेकिन then you have to be able to listen to the channel कि कोई और तो नहीं भेज रहा। चैनल जब खाली है तो आप भेजना शुरू करते हैं। अगर कोलिजन हो जाए, you have to stop transmission, you have to back off and then retry after some time. अब we'll come to that कि वो कैसे, how are you going to design this ताकि probability of collisions जो है ना वो कम हो, ठीक है। So is this clear? There's a trade-off here, but these are broad classes: channel partitioning,
Yes, sir.
random access.
Thank you, sir.
Okay, so random access protocols specify how you detect collisions, how to recover from collisions, and then there are some examples. Okay, so सबसे पहले एक system है which is called Aloha, and this was early 70s में Hawaii में they were doing transmission using a system of packet radio transmissions, and the different islands had these radio transmitters and receivers. And Aloha means hello in Hawaiian, and that's how the protocol got named. It's a random access protocol, and the assumptions here are that all frames are of the same size. Okay? Now, this is interesting because जब random access है, तो अगर frame size एक नहीं है, कोई बड़ी frames है, कोई छोटी frames है, तो obviously that adds further complexity to the system. So we're assuming that all frames are of the same size. Time is divided into equal size slots, and the slot is the time to transmit one frame. So this is slotted Aloha. So this is not simple Aloha. It's slotted in the sense कि आपके पास frames हैं, जो frame की transmission की duration है, that is the size of the slot. And then you have a synchronous system. You have a common clock, and nodes start to transmit frames only at the beginning of slots. तो हर slot boundary के ऊपर nodes transmit कर सकते हैं, ठीक है। nodes सारे synchronized हैं, तो they all know कि slot boundaries कहाँ पे है, and अगर दो या दो से ज़्यादा nodes transmit एक slot में, so the nodes are able to detect collisions, ठीक है। so अब वो कैसे होगा कि basically आपके पास while you are transmitting, you will be able to sense the channel, and if what you are transmitting is not what you're receiving, then you know that someone else is also transmitting and there is a problem. Okay. So the operation works as follows: that when a node obtains a fresh frame to transmit, it waits for the next slot to transmit that frame. And if no collisions take place, the node can send the new frame. And if a collision takes place, then you retransmit the frame in each subsequent slot with a probability P. Now, यहाँ पे what we're saying is कि आप next slot में उस frame को लाजमी नहीं भेजेंगे. You will transmit it with a probability P. Now, why is this? Because you were to definitely transmit it with probability 1, तो फिर तो ये है कि जब भी collision होगा, आप अगले slot में फिर भेजेंगे, वो दूसरा भी भेजेगा, फिर collision होगा. अगर आप probability P से भेजेंगे, and अगला भी probability P से भेजेगा, which means that you might or might not transmit that frame in the next slot, then there is a chance that in the next slot, maybe you transmit and the other one doesn't, or vice versa, or both don't transmit, okay? Or both transmit. All 4 of these possibilities are there. But if you or the other one transmits and the collision does not take place in the next slot, it will result in a successful transmission. So by varying this probability of transmitting in the next slot, choosing this as a design factor, okay, you can work out कि आपके पास क्या होगा. For example, nodes हैं आपके पास, पहले slot के अंदर तीनों ने भेज दिया, तो collision हो गया. अब next slot के अंदर, each one of them is going to transmit with the probability P. Now let's suppose for argument's sake that next slot के अंदर कोई भी इनमें transmit नहीं कर रहा. Obviously they don't know कि दूसरा क्या करेगा, ठीक है? ये हर एक node independently function कर रहा है. फिर next slot के अंदर node 1 and node 2 simultaneously transmit करते हैं, फिर collision होता है, ठीक है? So because it's a collision, it's not successful. Next slot के अंदर only suppose node 2 transmits and 1 and 3 don't transmit, so this is a success and this packet is going to go through. Next slot के अंदर suppose तीनों transmit नहीं करते, so it's empty. Next slot में once again 1 and 3 transmit, you have a collision. The next slot goes empty. Then 1 transmits, so it goes through successfully, and then 3 transmits, it goes through successfully. So they all had 3 frames to transmit. They all try to transmit simultaneously, resulting in collisions. Uske baad, they are transmitting with a probability P until success. ठीक है? तो ये इसने यहाँ पे ट्राई किया, collision हो गया, फिर ये चुप हो गया, फिर इसने यहाँ ट्राई किया, फिर collision हो गया, फिर ये खामोश हो गया, बैक ऑफ करके बैठ गया आराम से, फिर अगले स्लॉट में नहीं ट्रांसमिट किया, उससे अगले में फिर ट्राई किया एंड इस दफा ये सक्सेसफुल हो गया, इट गॉट थ्रू. Node 2 transmitted here, got a collision, didn't transmit here, transmitted here, got a collision, didn't transmit it again and got successful and got the packet through. So notice that you had multiple slots before these 3 nodes could successfully transmit one node, 1 frame each. Okay? But there is no need for sort of dedicating a particular slot. ये तीनों random पे ही चला रहे. They are trying to transmit at random. Okay? If a collision takes place, they stop. I mean, they transmit with the probability P in the next slot. So it's like running a random number generator and with a probability P transmitting in the next slot. If that turns out to be transmit करें, आप transmit करेंगे. If you're successful, well and good. If you aren't successful, you will again try transmitting with probability P in the next slot. Right? So any questions here? Slotted lower how it's working.
सर अगर इसमें हमारे पास एक से ज्यादा फ्रेम होंगे तो सर ये तो फेल नहीं हो जाएगा? सर ये तो देख के लग रहा है.
जी
सर मैंने कहा कि अगर हमारे पास एक से ज्यादा फ्रेम्स आ जाते हैं किसी नोड पे या फर्ज करें तीनों नोड्स पे, तो ये तो सर बहुत ज्यादा कोलिजन नहीं हो जाएंगे?
डिपेंड करता है कि आप P क्या चूज करते हैं. देखिए, अगर आप P को थोड़ा रखते हैं, लेट्स से प्रोबेबिलिटी ऑफ ट्रांसमिटिंग इन अ सर्टेन in the next frame is only 1/4, ठीक है, तो कोलिजन्स कम होंगे, लेकिन प्रोबेबिलिटी ऑफ ट्रांसमिशन चूंकि कम है, ठीक है, तो इट विल टेक यू अ लॉन्गर टाइम टू एक्चुअली ट्रांसमिट दैट फ्रेम. ट्रेड ऑफ हियर. यानी वंस अगेन, अगर आप P को ज्यादा रखते हैं तो प्रोबेबिलिटी ऑफ कोलिजन अगले स्लॉट्स में बढ़ जाएगी. अगर आप P को कम रखते हैं तो कोलिजन की प्रोबेबिलिटी कम होगी, लेकिन ट्रांसमिशन की प्रोबेबिलिटी भी कम होने की वजह से आपको ज्यादा फ्रेम्स लगेंगे टू एक्चुअली, ज्यादा स्लॉट्स लगेंगे टू एक्चुअली ट्रांसमिट दैट फ्रेम. लेकिन द ट्रेड ऑफ इज कि ये इट्स अ सिंपलर सिस्टम. इन द सेंस कि आपको कोई जो है ना ये चैनल्स एलोकेट नहीं कर रहे कि किसी का कोई डेडिकेटेड चैनल आप यहाँ पे नहीं रख रहे. लेकिन ऑफ कोर्स दिस इज स्लॉटेड. सो स्लॉटेड इज द एडिशनल कॉम्प्लेक्सिटी is कि आपके पास एक कॉमन चैनल है, कॉमन स्लॉट्स हैं यहाँ पे. So that is, यानी for reason of analysis, and you have slotted ALOA system like this. अगर ये स्लॉट्स ना होते which is called a simple ALOA system, तो फिर आपके पास क्योंकि स्लॉट्स नहीं है तो कोई भी किसी को ट्रांसमिट कर सकता है, तो ये आपके पास जो ओवरलैप है ना वो ज्यादा हो जाएगा कोलिजन्स के लिए. बिकॉज यहाँ पे कोलिजन ये एज चूंकि अलाइंड है यहाँ पे, तो कोलिजन सिर्फ स्लॉट के शुरू में ही है. उस केस में जब ये अगर आप स्लॉट्स खत्म कर देते हैं और कोई भी कभी भी ट्रांसमिट कर सकता है, तो फिर अगर कोई भी पोर्शन इसका अगले फ्रेम के साथ ओवरलैप करता है तो you'll have a collision. ठीक है? So your probability of getting through will become even smaller. ठीक है? But this is the trade-off. I mean, here we are designing a system which is simple. It is implementing a simple protocol कि भाई ट्रांसमिट करो, कोलिजन हो गया तो अगले स्लॉट में प्रोबेबिलिटी p के साथ ट्रांसमिट करो, फिर कोलिजन हो गया तो फिर अगले स्लॉट में प्रोबेबिलिटी p के साथ ट्रांसमिट करो. तो as far as the local system is concerned, it's not complex, it's simple, and it is achieving throughput. ठीक है, रेट कम है बट अल्टीमेटली कोई ना कोई सक्सेसफुल हो जाता है अगर कोलिजन नहीं होता, एंड उसका पैकेट चला जाता है, एंड ऑल थ्री ऑफ देम आर गेटिंग सम थ्रूपुट. तो इसकी एफिशिएंसी आप डिराइव कर सकते हैं. ठीक है, pros are single active node can continuously transmit at full channel rate. It's a highly decentralized, it's simple, but you have to be in sync. मसला ये है कि आप स्लॉट्स को जाया कर रहे हैं जैसे आप कह रहे हैं, एंड आपके पास बहुत सारे स्लॉट्स खाली भी जा रहे हैं, and nodes may be able to detect collisions in less than time to transmit the packet, and मसला ये है कि आपको क्लॉक सिंक्रोनाइज करना पड़ रहा है. So इसकी अगर आप efficiency derive करते हैं, you can do that very simply by using probability theory, and उसमें ये है कि if you know Bernoulli and binomial probabilities, it's the same thing that you have, suppose n nodes to transmit, each is transmitting with the probability p in a slot. The probability that a node is successful is n-1 failures के बाद एक success है. Probability of a failure is going to be 1 minus p to the power n-1, and then a success is going to take place with probability p. So therefore, this is the probability that one node has a success and all nodes have a success is going to be n times that, because they're all independent events. So what you want to do is you want to maximize this quantity here for p, and isko agar aap karen derivative leke or with respect to p and put that equal to 0 and solve that, you find that as the number of nodes become large, आपके पास the probability of success is 37%. So 37% is sort of the maximum in the limit. That's sort of the value at best that you can get. 37% useful transmissions आपको मिल सकते हैं. And यही काम जब आप unslotted ALOA के लिए करते हैं, pure ALOA के लिए करते हैं, तो आपके पास अब फ्रेम्स जो कि बाउंड्रीज अब नहीं है, ओवरलैप किसे भी हो सकता है. कुछ पोर्शन भी शुरू का भी या आखिर का भी ओवरलैप कर जाए तो आपके पास कोलिजन हो जाएगी. एंड इफ यू वर्क दैट आउट, तो it's exactly half the efficiency of slotted ALOA. So it's only 37 ka half, which is 1 over e. 1 over 2e is approximately 17.5 यानी 18% से भी नीचे आपके पास ही efficiency आती है for pure ALOA. ठीक है. So these were the first systems जो कि early 70s में डिजाइन किए गए थे for packet radio as well as for systems where you had a fixed frame size, and you either had a slotted system where you had common clocks, or you had a system where they could transmit at any time. You still achieved 18% efficiency, but if you didn't have too much data to transmit, you have a system which can transmit over multiple islands, and at that time it was perfectly valid because you didn't have too much data to transmit, and with a very simple system with no common clock, random access, you could get 18% efficiency in transmitting the thing. Okay, so any questions here?
Sir,
Gigi.
sir, in the unslotted case, why do we still have slots? Why do we still have time slots?
No, we don't have time slots in the unslotted case. All we're saying is that if we're assuming once again a fixed sized frame, okay? And we said, for example, agar ye node I hai, okay? So what is the possibility of an overlap? So let's suppose that the other frame, as long as it begins such that overlap ho jaye at the tail of that and the head of this, or koi और frame iske khatam hone se pehle shuru ho jaye, you have a collision. So if you're starting at T naught, then, and if your frame duration was, let's say 1, okay? If somebody started at T naught minus 1 or T naught plus 1, is window ke andar, yani this is a window of 2. Okay? So if your frame duration was 1, okay, as long as somebody started less than 1 frame earlier than you, 1 frame transmission duration, or started less than 1 frame duration after you, you're going to have a collision. Okay?
Right, sir.
So slots nahi hai yahan pe, lekin just for the analysis, you're assuming same fixed size frames of 1. If you start at T naught, then as long as somebody does not start in this window, T naught minus 1 to T naught plus 1, you will have no collisions. If they start T naught minus 1 ke baad, ya T naught plus 1 se pehle, theek hai, to collisions honge. Okay?
Right, sir. Understood.
Okay, okay, ji. Okay, so we'll stop here, inshallah, and we'll continue with this on Friday. Okay, assalamu alaikum.